So one of the most common forms of data analysis any um, in any study is just a scatter plot or a regression to look for a correlation between two continuous variables. So if both of our variables are continuous, then if we put one on the x-axis and the other on the y-axis, then it's easy to get a scatter plot like what you're looking at here. So panels A through F in these graphics uh, show you a variety of outcomes from a scatter plot. Anywhere from A shows a linear relationship that's positive with a little noise around a best fit line. B, of course, has no noise around a best fit line and is negative. Same with C, that's a perfect fit, which would have to be made up data really in almost both those cases. D is a parabolic fit. It looks like a parabola, like a rainbow. E has no pattern at all. It's a shotgun pattern, and there's no relationship. And then finally, F has a negative trend with some noise. There are associated correlation values around this, and the big difference that is important to recognize is a difference between talking about correlation versus regression. So when we're talking about correlation, our axes can be flipped and we're thinking about how two things are related to each other or co-related, if it helps you to remember it that way. But we are not thinking about one predicting the other. And so typically we use correlations value for that, and Pearson's R is a common correlation value that we've used for that, and there's a nifty little equation that we'll go through in a second that shows you how to calculate Pearson's R. But here you can just see different Pearson's R values, and the difference between Pearson's R and R squared, which I'm sure you've probably seen in previous biology or chemistry classes, is R squared ranges from 0 to 1, and Pearson's R goes from -1 all the way up to +1. And so you see in our first case here, we have a correlation equal to 0. There's no correlation. And then we have a slight negative correlation, which is a -3, a slight positive correlation, which is a 0.5, stronger negative correlation on the bottom left, -0.7, a positive correlation of 0.9, and then a negative correlation of -0.99, showing you a negative trend. So you get both direction of the relationship and strength of the relationship in a correlation value. And so that's looking at correlations. Regression, on the other hand, is a little bit different. In regression, we're using X values to predict Y values. So some readings really emphasize that they're not all that different when it comes to the score. The R squared really is just the R squared in most simple cases. However, there are some assumptions that go along with regression that are important. And there's a usefulness to regression that you don't find the same in correlation analysis. And that comes from developing an actual equation that allows you to predict Y from X. So here we have 3 X values, and then we have what looks like histograms, but they're turned on their sides, or what look like data distributions, but they're turned sideways. And that's done for an important reason. If we look across these individual points here, and my scribbles aren't coming across very clean, but try them again. If we have our data spread up and down this line here, what I've just drawn or tried to draw with some goofy little dots, which sometimes aren't even dots, are 6 points. And so 6 points evenly distributed within a distribution. The point of each of these is to show that there should be, in an ideal regression, actually a distribution of points at each level of x. So at the level of x, x2, I should have a number of points along the line here, and draw these now as hash marks instead of dots because it's working out better for me. And those points should be distributed so that most of them are going to be near the center point where the line crosses. And very few, only occasionally, you'll find one out at the margins of the distribution. So this distribution is turned on its side, but the point is most of the dots are going to fall where you see this largest part of the distribution, and then only a few to the side. So it's like a histogram just turned on its side. In each case, we would predict the value here as B1, some constant for the equation, the same one that's in our equation here, times our x2 value, plus B sub 0, which is the same B sub 0 that we have in our equation there. And then it has a variance. In this case, it's showing the population variance, but we would be more used to it from the way we talk about it, instead of sigma squared of s squared, right? And so there's an assumption here that all points for any given value of x along the x-axis, we have the same sigma squared or s squared, we have the same variance. So each of these distributions is going to vary in the same way. And then they're going to have a mean that is defined by the line of best fit. So, okay, a lot more to think about there. Basically, all this comes down to is saying your data should be equally variable along the fit. And in some of the examples that we saw before, let's see here. Let's see, those are our correlation scores, but we'll get back to some regression scores that are similar. Here are some good examples here where the variance along x, so if we have x here, we have our x-axis here. For any level of x, you can see there's kind of an equal spread of the data around a center line, or our regression line here. And that's happening no matter what the shape of the regression is. So that's really important. So these are different types of regression lines. There are linear regressions are the most common. This is the same equation form that we were looking at before, where it's usually a y equals mx plus b, or in the case of this one here, it's b sub 0 plus b1 times x, or b1 times x plus b0 instead of mx plus b. So it doesn't matter what we call those constants. They could be m, they could be b, they could be b prime or b1 or b naught, as they are here. Here's a regression that has some nifty little lines that help us understand variability. So the next thing I want to do is talk about line of best fit, and we're going to pick up here with this regression. All right. Here we have a line of best fit in this regression. And you may have wondered for a while what makes a line of best fit a line of best fit, or maybe you already knew, and if you did, this will just be a little bit of a review. But it's going to come all the way back to that old favorite chestnut, the variance equation. Oh no, I wanted to forget that. So we're going to come all the way back to talking about what is variance. And you'll remember back in variance, we had x sub I, like this, right? And forgive my handwriting. And then we subtracted off x bar, right? And then we realized that positive values would cancel values. This was when calculating the mean, and variance around a mean. And we realized that when we were trying to figure out how far away each x of I was from x bar, the mean, that we had a problem where negative values would cancel positive values. So to do something about that, we simply squared that, right? These were squares, right? And then we ended up dividing by an n-1 and doing some other stuff. But the first thing was just figuring out how far away each observation was from the mean, from the sample mean. And some of you may have seen this in other forms. We could also, because we're looking here at y axis, we could think of this instead as y sub I minus y bar. And in fact, for each of these points, you could think of calculating the mean of these points, or the dotted line that we have here, as a y bar. And then the points that we have here, these red dotted points that we have here, these guys, we could think of them as being calculated by taking our y sub i's, and each point would be a y sub I, and the distance from that point to the line, or y bar, this would be y bar, this is y sub, this is a y sub I, in this case it'd be y sub 26, but that's a y sub I. So we could take that y sub I and we could subtract off y bar, and we would get a negative number because y sub I is smaller than the mean, in this case, y bar. So in order to keep that, when we add all these, if we wanted to know what's the average distance, for example, of a point from its mean, and we'll ignore the line of best fit here for a second, we could say, okay, let's just add up all these distances. Let's look at all the distances of the individual black points from the mean, and let's add them all up. Now, but we have the problem that we did before when we were calculating variance, which is that they're going to cancel each other because we have negative values here and we'll get positive values here when we take an individual y sub I and we subtract off the mean. So what can we do? Well, we can square it, of course. Hence, squares. But let's think of that line instead as our mean. And if we take that, what we have here is a y bar here. And if instead of a y bar, what if we took that and we made it a y hat? And in that case, it would start to represent this line. This line gives us our y hats. And y hat would be the estimated value of y at the line. And so at any point on the line here, there's a y hat. And the y hat is the actual point along the line, not where the location is itself. So we could estimate the distance of those individual points to the line now instead of to the overall mean. And we could say, well, let's minimize the squares of the distance from those individual points to the line. And then we have a least squares regression.